Okay, so today we will start the discussion on a representation of alternating groups. So let's just recall what alternating groups are. So alternating group of degree n is which is usually denoted by an is a subgroup of symmetric group Sn. Yeah, so it consists of even permutations. So this, so as we know, every permutation can be written um, as product of transpositions, not necessarily disjoint, and then the number of such transposition is well defined. Yeah, so whether it's even or odd, not the number, but whether it's even or odd is well defined. And so if it's even, then we call it an even permutation. So I guess you know all this about alternating groups. So you take the set of all even permutations, so that's closed under group operation and the composition. So that's the subgroup, alternating subgroup. So one can also think of it as kernel of the sign map. Yeah. So we have given a permutation, we decide its sign, whether it's if it's even, you say it's 1. If it is odd, you say it's -1. Yeah. So kernel of this is precisely. Yeah. So now we want to study all the irreducible representations of an. Yeah. So we know what irreducible representations of Vn are. They are given by the Young tableau. Yeah. So let V lambda be an irreducible representation of Sn. So I mean, I've used lambda because that's what we were using. Yeah. So for lambda, so they are in bijection with Young tableaus. Yeah. So giving a irreducible representation of Sn, in general, what it means is you give a. So giving a representation means you have a map from Sn to GLV lambda, which we denote by phi lambda. So note that when we restrict this phi lambda to an, then what we get is an an representation on V lambda, yeah, which is also called the restriction, yeah, restriction from Sn to an, and is denoted by res Sn an V lambda. So of course this is a representation of an. And in general, so this may or may not be irreducible. If V lambda is reducible, there is no chance of it being irreducible. But if V lambda is irreducible, then it may be irreducible, but it may not. So we'll see that some of these restrictions are indeed irreducible. Yeah. So of course, if V lambda was one dimensional, then of course it is irreducible. You can't make it smaller. Yeah. So the trivial representation, alternating representation, they are of course all fine. Yeah, so you see that some of these will be irreducible, but some may not be irreducible. So that means some will be reducible, but you can say how bad it is. Yeah. So say W is the restriction of this representation. Then what you can say is W is direct sum of two irreducible representations of EF. Yeah. W prime and W double prime. So it's not. It's just a step away from being irreducible. So. And this is how you can get all the irreducible representations. So, okay, so we'll see this that this is, and then we will maybe relate it to tableaus as well. So a lot of this is not really Sn or An specific. It's about a group and containing a group G containing an index 2 subgroup in it. Yeah. So remember, En is index 2. Yeah. So because surjects on to ±1, so kernel is kernel is AN. So the index is precisely 2. Odd permutation and even permutation. So there are 2 cosets. So there is a lot of it, as I said, is holds true slightly more generally. So we will prove something slightly more general and then apply it to AN later. So let's any questions?
Yes, sir, could you just scroll up a bit, like just a bit?
Yeah.
Yes, sir. Just yes, thank you, sir.
Yeah. So yeah. So these are the 2 ways you can get irreducible AN representation. Either it is a restriction of a SN it is when you restrict irreducible SN representation, it stays irreducible, or if it doesn't stay irreducible, it decomposes into 2 irreducible representations. Okay. So these are the only ways, and there is some sort of unique. So I'll get to it once. So most of what I'm saying works for index 2, and then when we want to do it specifically for AN, then we'll bring in Young tableaus. So today we'll just prove something analogous to this in a more general setup. Yeah. So let G be a finite group, and H a subgroup of G of index 2. And then, of course, the first thing we know is that an H is automatically normal. Yeah, H is normal subgroup of G. So that we know. So now, if you are given, yeah, so there's 2 representations of G you get by looking at the quotient. Yeah, so and H is normal in G, and well, what is G mod H? G mod H is isomorphic to
Z mod 2Z.
Yeah, so maybe it's too obvious. Yeah, so nobody wanted to say. So it's Z mod 2Z. Yeah. So what are the 2 representations you can get of G out of this this observation? 2 straightforward representations of G. So one is the trivial representation. So note that now if you take any Z mod 2Z representation, it becomes a G representation. Huh? So you have a surjection onto Z mod 2Z, and any Z mod 2Z representation is a G representation as well. You just compose it. Yeah, and there are 2 Z mod 2Z irreducible representations. So there are 2 Z mod 2Z irreducible representation. One is the trivial one, and the other is the non-trivial one, the only non-trivial one. So you know how that works, yeah. So it's multiplication by minus 1. That's the only root of it. So the non-trivial element of Z mod 2Z acts via sending V to minus V. Yeah. So these are the 2 irreducible representations of Z mod 2Z, and this leads to 2 irreducible representations of G, because they're all both are one-dimensional. Yeah. So anyway, any irreducible representation of the quotient is actually an irreducible representation of the actual, even if it is not one-dimensional. But these leads to 2 irreducible representation of G. irreducible representations of G, which we'll denote by U and U prime, where this is the trivial guy, trivial representation, and this is what are the other composition, so the other one. So these are one-dimensional. Okay, and so what? So we know what chi U is. So the trivial representation is just 1 for all G in G. And what is chi U prime G? So what will be the chi of U prime of G, depending upon whether, so it should depend upon, so what happens if G belongs to H?
1.
1, yeah. So it is actually the homomorphism, right? So it's 1, and if G does not belong to H, then it is
-1.
Okay. So so the two representation of Z mod 2Z is homomorphism from Z mod 2Z to C star, and there are only two of them. One is everything goes to the identity element of C star, and the other one is you send 1 to -1 and 0 to 1. So this is how the characters of this look like. So now if I give you, so let V be an irreducible representation of G, then we know that we can get more, so so if you tensor it with U, nothing changes, because it's a trivial representation. But if you tensor it with U prime, then you get a new representation, and V tensor U prime, which we will denote it by V prime, is what kind of representation is also irreducible. Why is it irreducible?
The characters are this.
The characters are not, so V and V prime may not be same, the character might be different. But what's a quick way to check whether V prime is irreducible or not?
The product, like the inner product with itself.
Yeah, exactly. So you compute the inner product. So character of V prime is just character of V times character of U prime. So inner product, so if you do the inner product, it's just absolute value, right? So it doesn't matter whether it's plus something or minus something. So maybe I'll just, so these are some observations that you may have. So chi V prime, the product is just, by definition, it is 1 over size of G, chi V prime G, chi V prime G bar, where G belongs to G. But that, of course, is same as take the absolute value and then square it, So this, of course, is chi V prime G absolute value square, but I can drop the V prime now because, maybe, so since chi V prime is chi V times chi U prime. And chi U prime is 1 or -1. So if you do the absolute value, it doesn't matter. Okay, so they have the same absolute, which will be 1 if V is irreducible. Yeah, so that's the characterization of irreducible. Okay. So so V prime is also irreducible if V is irreducible. So yeah. So what else I wanted to say? Yeah. So there now also so I'm trying to write down. So I have told you this thing. Yeah. So I'm just developing some notation, etc., to write down that. Yeah. So now say W is an H representation. Then of course you can get a conjugate representation as well. So remember H is a finite index is a index 2 subgroup in G. Yeah. So when we were doing this induced representation, etc., we started this. Yeah. So for instance, yeah. So I don't know. Maybe I'll write down what is the conjugate representation. So that GB in G, then you have then step 5 first. What is the source? Maybe phi is an H representation, so it's given. So this corresponds to, let's say, phi from or yeah, phi from rho is what we were using. So let's just keep it rho from H to GLW. Okay, it's frozen. From H to GLW. So of course, what you can do is you can get another representation out of it depending upon G. So rho G from H to GLW, which is what you do is send H to rho of G, H, G inverse evaluated at W. So H going to maybe this matrix, yeah. So this linear map. Okay, so remember, I mean, this is again since H is a normal subgroup of G. G H G inverse is actually in H again, yeah. So this makes sense. Rho of this makes sense, yeah. So rho G is a conjugate representation. Conjugate. So actually, if G is in so maybe this is also a conjugate representation. So rho G is a conjugate representation. So remember, so this is so actually this is nothing about H being normal. So remember this: if you consider this in GHW, yeah. So in this we saw that W is a sub-representation, and so remember this is basically I mean if V was something like in GHW and then W, you think of it as a so when you think of V as a H representation, then W is an invariant subspace, yeah. So H invariant subspace. So so V decomposes as W plus so actually you can write it as direct sum of G W, where G belongs to G mod H. up to a left coset. Yeah. So of course, I mean, that is how the induced thing was. So of course, W is a H representation. But if I take G times W, then this also has a representation, but no, it's not an H representation. So you multiply by G inverse, then H, and then G, then it becomes a, so this is a G, H, G inverse representation. So in general, and this is a, so when, even if H is not a normal subgroup, this is GW is a GH, G inverse representation. And if this happens to be a H itself, then this is a GW is a H representation again. So, and this GW, of course, only depends upon the left cosets. Yeah. So it doesn't really depend upon G. Yeah. So rho G, so if I take, if G belongs to H, then GW is equal to W. Yeah. Rho G is isomorphic to rho. Yeah, so if G belongs to H, there is nothing. Yeah, so it you get the same representation. As a representation, they are isomorphic. If G does not belong to H, then rho G rho G is some representation which may or may not be. So I mean, it may happen that rho G is still isomorphic so rho G is still isomorphic to W. Then rho G. So what I want to say is, if you take two different guys, then they are. So maybe I'll write it. G does not belong to H, and G prime also does not belong to H. Then in this case, then G H equals G prime H, because there are only two left cosets. Yeah, and the one is H and the other one is not H. Yeah. So these two must be same. Hence, rho G and rho G prime are same, are isomorphic. So we can we can just say this is the, I mean, yeah. So it doesn't rho G only depends on the fact that whether it belongs to H or it doesn't belong to H. Yeah. So maybe I'll just call it rho prime, which will denote by rho prime. So yeah, I don't know if I want to call rho prime. Yeah, sure. I'll call it the conjugate representation. Yeah. So this is this will be called conjugate representation of W. So if it has index 2, then there is only one unique conjugate representation, which may or may not be isomorphic to the representation we started. Okay. If it has so you see this generalizes whenever you have H is normal in G, then it will have so many conjugate representations. Yeah. So it will have index of in G index H possible. So it may have up to that many distinct conjugate representations. So some of them may be isomorphic, so they may not all be distinct, but it cannot have more than G colon H and distinct conjugate representation. Here, So you can have at most one other. Yeah. But the conjugate representation in this case is given by this. So here you can take G to be any element not in H in our setup. Okay. So now, yeah, so maybe now this is all I need to have to state the theorem. So here it is. Okay, so let H be an index to subgroup of G. Let V be an irreducible G representation and W be the restriction of V to H. So, so there are two possibilities. One is that W itself is irreducible. So I said like in AN, so it's possible that W is irreducible. In that case, now what happens? So there are two possibilities: W is irreducible, W is reducible. Yeah. So when W is irreducible, we will see that V and V prime, which is remember is V tensor U prime. The U prime was that other representation you got. So it sends H to 1 and anything outside H to -1. That representation U prime. So V is not isomorphic to V prime as G representation. So they are actually distinct. And W is, in this case, W is isomorphic to its conjugate. Okay. So it's isomorphic to its conjugate representation. And the other possibility is that W is got to be reducible. So then what you can say is W is isomorphic to W prime plus W double prime, where W prime and W double prime are two irreducible H representation, and they are going to be conjugate and not isomorphic. So so W prime and W double prime are conjugate representations of H. So W double prime is, let's say, a conjugate, the conjugate representation of W prime, and they are not isomorphic. And if you induce W prime to G, you get V, or you induce W double prime to G, you get okay. So that is these are the two cases, and moreover, every irreducible H representation occurs this way. Okay. And also there is some sort of uniqueness, as I said. Also they occur this way uniquely. So V is missing here. This way uniquely, in the sense that in the sense that if V1 and maybe comma should be here or something. Yeah. If V1 and V2 are two irreducible representations such that V2 and V1 are not isomorphic, or V2 is not the conjugate of V1, then the irreducible representation you obtain in this way are non-isomorphic. So note that if V1 and V2 are isomorphic, then of course you'll get, if you apply the same process, you'll get its restriction is irreducible, and you'll get the same guy. So of course you want them to be non-isomorphic. Now, of course, but in the second, if you are in the first setup, then if you take V prime, yeah, the so you tensor V by U prime and take V prime, and if you restrict V prime also to W, then of course you'll get the same. You restrict V prime to H, then you'll get the same representation. Okay. Yeah. So maybe I should add that. So W is irreducible, and W is also equal to. So these are all easy observation. Okay. So W is the restriction of V prime as well to H. See, V and V prime, they sort of agree everywhere except, so they agree on H, yeah? There is no distinction between V and V prime on H. The distinction is only on things not in H, yeah? Because that is how the character also works. So they agree on, so that is why this works, okay? If they are conjugate, then in case if you tensor it by U prime, then this will lead to the same guys. But of course, if you yeah, so and sorry, so in this case, V is so in case 2, V is isomorphic to, so I didn't write that as well. So so maybe I'll write here. So in this case, V, in case 2, V is isomorphic to V prime. Okay. So in case 2, V is automatically isomorphic to tensor with U prime. So does this make sense? The proposition, is the statement clear of the proposition before we get to the proof?
Yes, sir.
Yeah. So let's see the proof. Yeah. So proof. So we will we'll start with. So we know that V is an irreducible representation of V. So we'll use character theory. Yeah. So main thing is using the character. Yeah. So V is a, so we'll have chi V is character of V. And what do we know about? So since V is irreducible, what do we know? We know that this is 1. Yeah. Yeah. This is maybe this is 1. Yeah. So if you this inner product is 1, which if you write it in terms of what it means, then this is same as saying size of G is equal to direct sum G in G of chi Vg whole square. Okay, but we can split this. Yeah. So and remember, G size of G is same as size of 2 times the size of H. Yeah, because we are in the index 2 set. 2 times size of H. And we can, so we want to restrict it to W. So somehow we want to see what happens to collection G in H, chi Vg whole square, okay, plus summation G naught in H. Stopped writing again for some reason. Chi Vg absolute value whole square. Yeah. Now what is this guy?
The size of each times chi W.
Yeah. So so this is basically character of W is chi of V restricted to W, restricted to H. Yeah. So this is the character of W in some sense. Yeah. So maybe one can put it this way. So this is just chi of W, chi of W H. But if we had divided it by H, yeah, 1 over size of H. So you just multiply it by size of H, right? So this is what it is. And what do we know about this number? This has to be, sorry, so I have to, yeah, maybe. Oh God. Sometimes it just starts acting. Yeah, so size of H, maybe I'll write it in front itself. Yeah. So this number chi w, the inner product of chi w with itself, this is going to be some integer. Yeah. So it depends upon how many copies w decomposes into. Yeah. So remember, if w is summation n1 w1 plus nm wm, and then what is this guy? By that orthogonality of characters, this is going to be summation ni square. Yeah. So w1 is inner product of w1 with itself is 1, and with other guys is 0. Yeah, so you get this. So this is going to be an integer, and this is also some non-negative number. So the only possibility for this some non-negative number. So only possibility for this is either this can be h, or it can be, and it has to be positive integer. Yeah? So it's either 1 or 2. Yeah, it can't be anything else because it's bounded by 2h. Yeah. So chi w is 1, or chi w is 2. Okay. So this implies w is irreducible H representation. So we are in case 1. Okay, and this implies that so if it is 2, then the only possibility is the m is 2 and n1 and n2 are 1. Yeah, so this implies w decomposes as two irreducible representation. W prime dxm w double prime, where w prime and w double prime are irreducible. Okay. So these are the two possibilities. So this is case 1 and this is case 2. Yeah. So in case 1, so let's just complete the picture. So in case 1, what happens? So we'll have to prove various other statements of case 1, and then the moreover part also we have to. So in case 1, in case 1, so of course W is irreducible. So what so I have to say this so that V and V prime are non-isomorphic. Yeah. So W is irreducible. Then yeah. Then these are this is non. So then V prime. So chi V prime. Chi V prime of so the point is this is not going to be 0. Yeah, so maybe then chi Vg is non-zero for some g not in H, right? Because this sum is only H and the total has to be 2H. Yeah, so this can't be all 0, which implies chi V prime G is not equal to chi V G for that G. Yeah. So which implies V is not isomorphic to V prime. Where V prime is V tensor. So so chi V prime G is going to be negative of chi V G if G does not belong to H, and hence they are not going to be same. Yeah. So that is this statement as here. W is isomorphic to its conjugate representation. And yeah, so of course, note note that V prime restricted to so chi V chi of restriction of V prime to H is same as chi of restriction of V to H. Yeah. So that tells you that that proves the statement that W is so this is also W. So this implies W is restriction of GH V prime. So V prime and V restricts to the same irreducible representation in this case. And yeah, so what was, so I also, we want to say that W is isomorphic to its conjugate. Yeah. So why is that? So W, yeah. So yeah, so maybe this one can use the yeah, so W is what? W is less GHV. Yeah, this is the restriction of V to H. And if you do the induced guy, then so that is W. And if you do the induced guy, what will you get? So so you'll get yeah, so what you get is W and W and its conjugate. Yeah. So this is in general W so this is how induced representations are made. Yeah. So W plus conjugate of W, conjugate representation of W. Okay. So this is what you'll get when you induce it. Yeah. So so now from here, I want to say that the conjugate representation should be same as W. So why is that? So I thought one could just use character theory. I mean, one can try to do this directly as well, but one can use So yeah, so maybe I'll come to it. So probably 1 second. So chi v comma w. So I'm trying to use some reciprocity. So and yeah, so maybe I'll get to it. Yeah, let's prove the other properties of case 2, and then we'll come to this. Yeah. So in case 2, so I will check this. Now where's this? So in case 2, what happens is so of course we already saw that W is isomorphic to W prime plus W double prime, which are both irreducible, and in this case. In this case, what happens is this is 0. Yeah, this term will be 0. Okay, so so the other sum is 0. So that tells you that so in case 2, chi v of G is 0 for all G not in H. Yeah, so this tells us that chi v prime, which is chi v time chi u prime, is going to be same as chi v. Yeah, since they on elements outside H, this is going to be 0, and for elements inside H, chi u prime H is just 1. Yeah, so these two are same, which implies that V is isomorphic to V prime. Yeah, so that the small thing which we had forgotten is there, and yeah, so then we want to show that W prime and W double prime are conjugate. Yeah, so maybe this is the part which is so yeah, so I want to show W prime and W double prime are conjugate. Conjugate representation. Yeah. And then, of course, and then it follows that the induced representation. So if you want to induce W to and W prime or W to G, then you'll get the other then it follows that int GH W prime equals int our conjugate non-isomorphic representation, and then it will follow that W prime is equal to V, because V is going to be W. I mean, it is going to be the induced representation is going to be W prime direct sum W double prime. There are only going to be two terms, and the direct sum is equal to V. Yeah? Is equal to W, but W as a space is same as V. So you get that V representation as G representation. Okay. So the only thing missing is to show that these two are conjugates and non-isomorphic, and to show that W and W is the conjugate representation of W is itself. Okay. So yeah. So it's it sort of is related to analyzing this guy. Yeah. End of rest. So let me just forget G and H. Yeah. So you restrict V to H, you get W, and then you induce it back to G. Then what is this guy? So so it's going to be sort of two copies of V in some sense. Yeah. Yeah. So I think yeah. So this is going to be V direct sum V prime. Okay. As G representation. So claim this is what we will get. So once we have this, then maybe it won't be too bad. Yeah. Then of course restriction of V prime is also W, and restriction of V is also W as H representation. So those two are isomorphic. Okay, so let's see why this is true. So yeah, so maybe they have the same character. Yeah, so maybe the check that they have the same character. So maybe I'll put it as a homework. So check that they have the same character. Same character. So we know what the character of restriction of V is. Yeah, you just restrict it to H, and then for induced representation we had a formula. Yeah, how to compute the character. So you will see that it will turn out to be, so on elements of H is just the yeah. So it will turn out to be this guy. Okay. So maybe home. And so from the claim implies in case one, that if that conjugate of W is W. So the point is, so if you see, the point is W itself is a G representation. Yeah, I mean there is an action of G on W. So maybe all this thing is not really. Yeah. So it is sort of self conjugate. Okay. So there is. So remember this when we were trying to do this conjugate representation. If you conjugate by an element of G itself, then you get you conjugate by an element of H itself. Where is the conjugate? Here. Yeah. So if you conjugate by an element of H itself, then you recover the same guy. Yeah. So here W happens to be V representation itself. So this is not that surprising. Only if so W prime and W double prime are not really a G representation. It's actually an H representation. You can't. There is no action of G on W prime. So that's why. They will so that's why they are going to be different. Yeah. So maybe I'll finish this part the remaining part of this next time. So I'll finish I'll prove this next time, this part, and the moreover part next time, the moreover meaning every irreducible representation of H occurs this way. So that's some general nonsense. And then so this part is not difficult, and then we will use the Young diagram to Young tableaus to say something specific about AN representation as such. So list down AN representation in terms of Young tableau. Okay. So maybe I'll stop here, and next time I'll complete the proof of this thing and use it to sort of describe all the irreducible representations of alternating groups. Okay.